Okay, the next section, 9.4, is called improper intervals, infinite limits. Infinite limits. You're going to decide, looking at these infinite limits, if they converge or if they diverge. 9.4 is not an easy section. You might want to watch this twice. This is leading on to the next chapter 10. The next chapter 10 is all about series that converge or diverge. It's probably one of the toughest things in calculus is chapter 10. You just have to get through one chapter in BC. This is leading into it. This will take me a while to explain all these problems. And you'll probably need 3 to 4 days, probably 4 days to do this assignment. So, if f of x is continuous from a to infinity, then this is true. A to infinity, sum f of x dx. Okay, all of these, you're going to find the limit as b approaches infinity from a to b, sum f of x dx. The second one, if f of x is continuous from a negative infinity to b, then you go from a negative infinity to b, sum f of x dx. You're going to find the limit as a approaches a negative infinity from a to b of x dx. And the last one, if f of x is continuous from a negative infinity to a positive infinity, you're going to integrate from a negative infinity to a positive infinity, sum f of x dx, which is equal to, you're going to integrate from a negative infinity to c f of x dx, and then you're going to integrate from c to infinity, sum f of x dx. Okay, I know this seems very confusing, but after we do some problems, I think you'll catch on. So basically what we are doing today is this. We are going to figure out if the limit exists. First thing you're going to do is you're going to integrate it by all the different ways that you know how to integrate. After you integrate it, if the limit exists, and after you integrate it and it converges, if it fails to exist, then it's going to diverge. And this is for the first two. The third one up there, if the left side converges and diverges, has no value. And then it will diverge, obviously. If the left side converges, but the right side diverges, then obviously you're not going to have a limit, a value. Okay, let's do some examples. I've got I think I've got 7 examples to do, different types of examples. So here we go. Example number 1. If you go from a negative infinity to a positive infinity, and you've got e to the x dx. Okay, so how do you set this up? So you say the limit as b approaches a negative infinity, and when you integrate that, you're going to get e to the x from, oops, let me start one. Oh, let's maybe one up here instead. We're going to integrate the limit as b approaches a negative infinity from b to 0 of e to the x dx plus the limit as b approaches infinity from 0 to b e to the x dx. So I'm doing this one first, and then I'm going to do the limit as b approaches infinity of e to the x from 0 to b. So when I plug 0 in, I'm going to get e to the 0 minus e to the b plus e to the b minus e to the 0. Okay, so e to the 0 is 1, so I'm going to be left with 1 minus e to the b plus e to the b minus 1. So when you do this, and when you plug in a negative infinity in for b right here, you plug a negative infinity in, basically what do negative exponents make? They make fractions like this, 1 over e to the negative infinity. It changes to positive. Okay, so as e is getting bigger and bigger, this is getting closer and closer and closer and closer to 0. So the only thing you have left is a 1. When you plug e to the infinity minus 1 in here, this is just getting bigger and bigger and bigger. And if you subtract 1 from it, it's still going to get bigger and bigger and bigger. So if you add 1 plus infinity, it's definitely diverging. Diverges. Okay, let's do another one. Let's do number 2. Let's go from 1 to infinity, which is a number, the top one. I just did the third, the rule. Now I'm doing the first rule from 1 to infinity. Dx x. And you're trying to decide if it converges or if it diverges. So the first thing I'm going to do is I'm going to write the limit as b approaches infinity from 1 to b of dx over x. And where did I get this from? I got this from the first one. I know they use a, b. They use some a to infinity. The a for me was 1, and I'm still going from b to infinity. Okay, so then what happens is, instead of a to infinity, it changes from a to b, because in place of the b, you put that infinity. So here we go. The next thing I'm going to do is I'm going to find the limit as b approaches infinity. And this is 1 over x, and when you integrate 1 over x, you get the natural log of x from 1 to b. And then I'm going to go down here and go limit as b approaches infinity. The natural log of b minus the natural log of 1. The natural log of 1, most of you know that is 0. So the only thing I'm going to do is the natural log of infinity. And the natural log of infinity obviously is infinity. So definitely it diverges. Okay, the next one. The third one, it's called a partial fraction. And I don't know if you did this. I think you did it in college algebra, but you haven't seen it since. If you're integrating from 0 to infinity, 2 over x squared plus 4x plus 3 dx. Okay, this is going to be time consuming. Okay, if you brought this up it's going to be x squared plus 4x plus 3 to the negative 1 with a 2 out in front, correct? If I integrated that, you need to add 1 to this, which makes 0, which makes natural log. But you also have the inside of that. So, and you don't have that on the outside. You don't have the derivative of the inside, which is 2x plus 4. So if you see this, and you see a huge fraction in the denominator, a polynomial in the denominator, you need to use partial fractions to solve this problem. So basically what you're going to do is algebra backwards. So this part is just algebra. So this is what you're going to do. You're going to write this down. You're going to factor this as x plus 3, x plus 1. And you're going to rewrite this as two partial fractions. I'm going to put the x plus 3 down here and the x plus 1 here, or vice versa. It doesn't matter which way you do it. It really doesn't matter. So you can put the x plus 1 here and the x plus 3 here. You're going to put an a up here and you're going to put a b up here. So what are we doing? We're taking the full fraction and breaking it up into two fractions. So you're going to multiply all of this by x plus 3, x plus 1. And when you do that, these two cancel each other out, so you're left with just a 2 on the left-hand side. When you multiply this by the second fraction, the x plus 1s are going to cancel out, but you're still going to have an a and an x plus 3. And when you do this times this, the x plus 3's cancel out, and you're going to have a b with an x plus 1. Then what you're going to do, okay, I'm going to start again. This is called a partial fraction. This isn't algebra. This isn't even calculus. You're going to take a fraction, and you're going to break it up into two different fractions by factoring the denominator. Part of the denominator goes here, part of the denominator goes here, and then you just use two different variables, a and b. Then you're going to multiply every fraction, the first one, the second one, and the third one by the common denominator, which is x plus 1, x plus 3. And by doing that, you're going to get rid of your fractions on the bottom. So that's what we have left. Then, you're going to let x equals a negative 3, and you're going to let x equals a negative 1. You're doing that so that you can get rid of your a's and b's. So let's, in place of x, let's put a negative 3 in first. So you're going to get a 2 equals. When you put a negative 3 in there, you're going to get 0, and 0 times a is 0. But when you put a negative 3 also in there, you're going to get a negative 2b. So b must equal a negative 1. Then, you're going to plug in x equals a negative 1. So you're going to write 2 down. And in place of all the x's, you're going to put a negative 1, which gives you a 2a. But when you plug a negative 1 into the last one, it's going to come out to be 0. So a equals 1. So now I can replace it, and I wrote my partial fraction. So a is 1, so 1 over x plus 1, and b is a negative 1 over x plus 3. Okay, if I wanted to put this back together like you learned in Algebra 2, if I wanted to simplify this, could I go back in a circle? If I want to put this as one fraction, don't I have to find the common denominator? Isn't the common denominator both of them? Isn't it x plus 1, x plus 3? And then you look, this one's missing x plus 3, so you have to multiply the numerator. This one's missing the x plus 1, so you're going to multiply it by x plus 1. And what you're going to have is what we started with. I'm just going in a circle. You don't have to. You're going to get a negative x and a positive x cancel each other out. And 3 minus 1 will give you 2. So I'm just showing you that you can break this up into two partial fractions. Okay, so now that we have it broken up into two partial fractions right here, I'm going to use that instead. So I'm going to integrate from 0 to b, the first one, 1 over x plus 1 dx. and then plus, and I'm going to integrate from 0 to b, a negative 1 over x plus 3 dx. And now, 1 over x plus 1 ends up being the limit, as b approaches infinity, of the natural log of x plus 1 from 0 to b, plus the limit, as b approaches infinity, of, let's switch this from a positive to a negative, and now I'm done with that being a negative, and that makes it a little bit easier. The natural log of x plus 3 from 0 to b. Okay, so now it's starting to become harder. I'm going to put in the b, so I'm going to have the natural log of b plus 1 minus the natural log of 0 plus 1, which is 1. Okay, so I'm done with that one. Minus the natural log of b plus 3 minus the natural log of 3. Okay, let's try to simplify this. This is the natural log of b plus 1 minus the natural log of 1 minus the natural log of b plus 3, and 2 negatives equal a positive natural log of 3. Okay, I'm hoping you know that this ends up being 0, so that's gone. So you have only 3 left. I'm going to combine these two because of the laws of the natural log. So the natural log, and when you have a minus sign in between, I can divide these, plus the natural log. And remember, I still need to do the limit as b approaches infinity. I haven't done that. So as b approaches infinity, think about this now. This is always going to be a little bit smaller than this. So this number is always going to be smaller than this. So that means that this part is getting closer and closer to 0. And 0 plus the natural log of 3 is the natural log of 3, which ends up converging. Converges. I know BC is definitely harder than AB. You might have to take a look at these notes over again. Okay, the next one is, which problem are we on here? Problem 4 is L'Hopital's rule. So I'm going to show you L'Hopital's rule. If we're going to integrate from 1 to infinity, x e to the negative x dx. Do you notice that this is the product rule? We have to learn how to do the product rule backwards. So I'm going to go over here and make myself my chart. This is the derivative, this is integral. And I'm going to put x here, and I'm going to put the e to the negative x here. The derivative of x is 1, the derivative of 1 is 0. The antiderivative of e to the x is a negative e to the negative x, which ends up being a positive e to the negative x. Positive, negative. So, I'm going to integrate the limit as b approaches infinity of a negative x e to the negative x from 1 to b plus positive okay, so yes, that's not going to be a positive. It's going to end up being a negative because of the sign. E to the negative x from 1 to b. Okay, so this is going to give you the limit as b approaches infinity of a negative b e to the negative b minus a negative 1 e to the negative 1. And then you're going to put a minus e to the negative b minus e to the negative 1. Wow. Okay, so that's going to end up being, okay, I'm going to put like terms together. So I'm going to put these two together, and I'm going to put these two together. So I'm going to take out an e to the negative b of the limit as b approaches infinity. And I'm going to be left with a negative b minus 1 plus, these are both positive 2 e to the negative 1. Okay. As b keeps getting, remember this is a negative infinity, that's a negative b, so it's going to be really 1 over e to the b power, negative b minus 1 plus 2 over e. Okay, as the limit as b approaches infinity. Think about this, as b is getting bigger and bigger and bigger, isn't this getting closer and closer and closer to 0? And 0 times anything is 0, so this whole thing is 0. So you're left just with 2 divided by e. So it converges. Okay, the next one, number 5. 0 to 3 dx over x minus 1 to the 2/3 power. Okay, now it's getting harder, and as you can see, if you graph this, it's discontinuous at x equals 1. So what do you do with discontinuity? So we need to go over improper integrals with infinite discontinuity. So let's go through the rules. So let's add another rule, and let's go through all the definitions of improper integrals with infinite discontinuity. So here are the 3 rules. You're integrating from a to b, f of x dx. You need to do the limit as c approaches a from the right, integrate from c to b, f of x dx. Then f of x is continuous from a to b. The second rule, if you're integrating from a to b, f of x dx, you need to do the limit as c approaches b from the left of a to c, f of x dx. Then f of x is continuous from a to b. And the last one, from a to b, f of x dx. If you integrate from a to c, f of x dx, and if you integrate from c to b, f of x dx, then f of x is continuous from a to c union with c to b. Okay, these are the definitions. All they're saying is you need to look on the right or on the left, or you need to break it up where it's discontinuous, like C is where it's discontinuous. Okay, so let's go back to this problem, and it's discontinuous at x equals 1. So this is what you have to do. We're going to use the third rule, and we're going to integrate from 0 to 1 dx, x minus 1 to the 2/3. And we're going to integrate from 1 to 3 dx over x minus 1 to the 2/3. So it's discontinuous at 1, so I broke it up in that spot. And now I'm going to integrate this. So before I do that, I think I'm going to bring this up. And I'm going to do the same with this one. Okay, so what I'm going to do is I'm going to look on the left side as x is approaching 1 from the right. And this one, I'm going to look at the limit as x is approaching x. Let's see. Start again. As c is approaching 1 from the left, and this is c approaching from the right. Okay, if you drew a picture of this, there might be one in the book. If you go from 0 to 1, you're approaching it from the left. If you go from 1 to 3, you're approaching it from the right. And when you integrate that, you're going to add 1 to this, and you're going to add 1 to this, which is 3/3. And 3/3 is 1. So you're going to end up getting, no, you're not going to get, you're going to get 3/3 minus 2/3, which is 1/3, which ends up being 3 x minus 1 to the 1/3. And then same thing with this one, 3 x minus 1 to the 1/3. You add 1 to this, just to let you know, you're going to get 1/3. The 1/3 goes here, but remember when you divide by 1/3, you're really multiplying by 3. Okay, so if you put 1 in there from the left, as you're approaching 1 from the left, you are going to integrate. I just did that from 0 to 1. This one you're going to integrate from 1 to 3. So you're going to plug 1 in here. When you plug 1 in here, you're going to get 0 minus, you plug 0 in there, you're going to get a negative 1 to the 1/3, and you're just going to end up getting a minus of a negative 3, which ends up just being 3. Over here, you're going to plug a 3 in there. When you plug a 3 in there, you're going to get 2 raised to the 1/3. And then minus, when you plug a 1 in there, you're just going to get 0. And this is the same thing as 3 times the cube root of 2. And plus. So it is converging. Converging. Okay, number 5, number 6, one more. If you integrate from 1 to 4 dx over x minus 2, you're going to see the picture, and it's discontinuous at x equals 2. So I'm going to integrate from 1 to 2, x minus 2 to the negative 1 dx, I just rewrote it, plus, then I'm going to integrate from 2 to 4, x minus 2 to the negative 1 dx. Okay, this is going to be the limit as c approaches 2 from the left, and this is going to be the limit as c approaches 2 from the right. When you integrate that, if you add 1 to it, it's the natural log of x minus 2 from 1 to 2. This is the natural log of x minus 2 of 2 to 4. So when you plug 2 in, you're going to get 0, the natural log of 0. Put 0. Minus the natural log of 1, the absolute value, plus the natural log, if you plug 4 in there, you get the natural log of 2, minus the natural log of 0. And when you get the natural log of 0, minus the natural log of 1 plus the natural log of 2 minus the natural log of 0. Okay, this is kind of deceiving, but what happens is when you graph this, it's going to end up diverging at the 2 marker because it keeps getting bigger and bigger. So if you look on page 468 at this problem, this is kind of a difficult problem because what happens is at that graph it gets closer and closer to a negative infinity, which diverges is at 2. Okay, I think we are done. I just have to write down the direct comparison test, and I'll show you one more thing. It's called the direct comparison test. This is comparing 2 of them. Number 1, well, first of all, before we start with number 1, you're going to let f of x and g of x be continuous on a to infinity. Then, if you go from a to infinity, if f of x dx converges, if only a to infinity, g of x converges. And the second one, a to infinity, if f of x diverges. If a to infinity of f of x dx diverges. There's one more. It's kind of like number 6, where you get all the way down and it's too hard to figure out, so you have to look at its graph. There's one more in the book, problem number 7, which is you're integrating from 1 to infinity e to the negative x squared dx. This is one where it's kind of, you can't do it algebraically, so the only way you can do it is graphically. And if you look, it does converge. It's on page 469. There's a picture of it. And it shows you that it supports it graphically, that there is a value. And just read through page 469, it'll explain that you can't do this algebraically. We don't know how to integrate this. You can't even use U substitution. It won't even work. So you'll have to do it graphically to figure out if it converges or diverges. Again, this is a tough section. There's a lot of work because you have to show all those steps, figure out if it converges or diverges.